This is how light is used in chemistry. We have a sample matter. Incident light falls on it is characterized by its wavelength lambda and intensity I. Then some part of light is absorbed by the material, some part is transmitted. We represent the transmitted light by intensity I prime, which is less than I, and wavelength lambda. Wavelength doesn't change. And a part of light may be scattered. The scattered light intensity is represented here by I double prime. And if the scattered light has the same wavelength as that of the incident light, we call this scattering as Rayleigh scattering. And if it is different from that of the incident light, we call this as Raman scattering. Now I make some statements which should be accepted, I think, this will be accepted by all. Chemistry deals with molecules. This statement we all agree. And chemists synthesize molecules according to the design. In the beginning of the creation, only small molecules like water, carbon dioxide, ammonia was produced. But with the progress of time, larger molecules, for example proteins, with complicated structures were synthesized. This we all know. Surprisingly, these molecules with their apparent complicated structure have some functionality associated with them. We know that protein has some special function in our body. Different proteins have different special functions in our body. Now, about the molecules. What is the similarity between the molecules? Molecules have different structure. Every molecule has a structure, and it has some special function. It's particularly relevant in biological systems. And there are other two things, for the interactions and dynamics. The structure, this molecule interacts with the other molecules in the environment and the surroundings. So how the structure interacts with the other molecule is also important, and this structure has also a dynamics. This is not a static structure, it has a dynamics. The molecule in fact moves in time, and this interaction dynamics control the function of the molecule. They determine the function of the molecule. Now, in order to have some information about this interaction and the dynamics of the molecules, there are two possibilities. One can calculate theoretically using some models and some equations. One can calculate some quantities, but the difficulty is that the theory ultimately gives some numbers, and one cannot, this is a molecular picture, this is a microscopic picture, no doubt, but this is not verifiable, or this is not verified by experiment. This is the difficulty. On the other hand, experiment is performed with the macroscopic substance, and they also provide some numbers. But how these numbers are related to the molecular picture is not, or the microscopic picture is not very well understood. So one hits a bridge between the theory and experiment, and there are, in fact, spectroscopy provides a bridge for this purpose. If we study the development of spectroscopy, it has developed parallelly. One is the experimental side, the hydrogen atom spectrum, discovered different series and all this from hydrogen spectrum to molecular spectrum. Experimental part, and on the other hand, the theories also emerged parallelly. For example, the first theory in spectroscopy is the Bohr's theory. And then after the advent of quantum mechanics, the spectroscopic process of spectroscopic transitions can be explained to you. So today's discussion will be mainly the spectroscopy, because this will help understand the relation between the structure and the function. Now, chemistry deals with the interaction between molecules, and we divide any change into physical change and chemical change. What is a chemical change? We define as a chemical change as a change where new substance is formed. For example, hydrogen reacts with oxygen to produce water. Water, and that is hydrogen, disappears from the system, oxygen disappears from the system, and a new substance, water, has been produced. This is a chemical change. And all the chemical changes are basically of two types. One is oxidation reduction type, where removal or addition of electrons or electron transfer process is important, and the other is the acid-base reaction, where the sharing of electron pair is important. Now, what about photoelectric effect? Is it a physical change or a chemical change? According to our definition, that chemical changes produces some new species. Matter and light, and electrons are being produced, but electrons are not there as the reactants. So, this is something like a chemical change, and this was first light disappears and new electron is created. Einstein first realized this, and he explained the photoelectric effect we know in 1905. He considered light composed of small particles. Now we know that these particles are known as photons. Einstein gave the name light quantum. And in this sense, photons are the molecules of light. They are the smallest part of a substance. Molecules are the smallest part of a substance that can exist independently. Here also, light photons of the light quantum is the smallest part of light, that can be considered as the molecules. Now, spectroscopy deals with the interaction of light with matter. For light, historically, Newton gave the corpuscular theory, and we have Maxwell's electromagnetic theory, then Einstein's quanta. And matter consists of atoms or molecules with quantized energy levels. And nature of interaction we should discuss. Now, photon, brief history. 1905, Einstein just gave the concept, put forward the concept of photons. His argument was very interesting. He argued like this: when we study the motion of bulk matter, one did not consider that it consists of atoms or molecules. It obeys Newton's laws, etc., etc. Similarly, when you study the bulk properties of light, for example, reflection or diffraction or things like that, these are the bulk properties. But if we consider this reaction photoelectric effect, which is like a chemical change, one must apply the concept of chemists, the concept that is chemists are using, that matter consists of smallest particles. That is, whenever we explain a chemical reaction, when new substance is produced or something disappears from the system, one has to use this molecular concept. And that is why this was the argument put forward by Einstein, a very interesting argument that light must consist of this, for explaining this event of photoelectric effect, one has to consider that light consists of smallest parts. In 1913, Bohr gave the condition that when this transition takes place between two states, the energy of the final state minus the energy of the initial state equal to h nu. But he did not postulate the light quantum. Light quantum was not mentioned. Just given this condition was used, this is the Bohr condition. In 1917, Einstein gave a mechanism of absorption and emission. Soon after that, there was Becquerel's theory. Both Kramers and Slater. In fact, both didn't believe in this quantum, light quantum. He tried to, these three, Becquerel, Bohr, Kramers and Slater, they tried to explain the absorption and emission in terms of the wave theory of light, and they were successful. But in the derivation, there was an assumption that conservation of laws, like the conservation of energy and conservation of momentum, need not be obeyed at the molecular level, at the individual event, when light absorbs or emits, or matter absorbs or emits radiation. These conservation laws has to be obeyed only statistically. And when Einstein was asked about the reaction on this theory, I said it cannot be. It cannot be true. If this is true, then I will just give up physics. I will not study physics anymore. If this is true, the conservation laws are violated, I will be a cobbler or a waiter in the casino, not a physicist. This is true. So much was the conviction of Einstein about the conservation laws. Then we know that in 1923, compound effect was discovered, and this proved the existence of light quantum. And in 1924, G.M. Lewis, a physical chemist, American physical chemist, who gave the idea of electron pairs, etc., electron pair bonds, etc., he gave the name photons to light quantum. So from 1905 to 1904 is a long journey. There is a period of beliefs and disbeliefs, and then in 1923 it was proved definitely, and in 1924 it has been named. We know now that photons have energy in h nu and momentum in h nu h c, and each polarization each photon is characterized by state of polarization. This is resolved. Now, if we consider the photons as the molecule of light, then a chemical reaction means molecules plus molecule produce molecules. This is a chemical reaction. A plus B produce C, A, B, C are molecules. So does this process take place? Photons, two molecules. We have photons, then they react or interact chemically to give molecules. No, we do not know of this example. Then does this process happen? Molecule plus photon giving molecules. All molecules, two molecules per photon, reverse case. Or two photons combine to give a third photon, different photon. Is it possible? We shall discuss. Albert Einstein, he gave the mechanical absorption revision. The idea of Einstein was that if there are two levels, one is the excited state with a higher energy and the ground state with lower energy, then N1 and N2 the number of molecules in these two levels, so then N1 and N2 is determined given by Boltzmann distribution at equilibrium, and absorption according to Einstein. Just look at the year 1917. In 1913, Bohr's theory was discovered. Bohr put forth the theory, and according to Bohr's theory, there exists some stationary states, ground and the excited states and the stationary states. Einstein utilized that concept, and when it is in the ground state, it should remain the ground state according to Bohr model. It is a stationary state unless it is disturbed. So this, to move to the excited state, it needs some push, needs some disturbance, and that push is given by light. So light pushes the molecule up to the excited state, and its state, it can come back to the ground state. That time, it was assumed that molecule in the excited state will automatically come to the ground state. This is a spontaneous process. So the emission process was considered as spontaneous. But Einstein added another mechanism for the emission process. He assumed, besides some spontaneous emission, induced emission process. Induced emission process, this will depend on the density or intensity of light. This is dependent on light. But this process was not known. This was proved only in 1960 and 1961 after the discovery of laser. But if we consider the Bohr model, then spontaneous emission cannot be there, because in the Bohr's model, excited state is also a stationary state. So, if a molecule is in the excited state, how can it change energy and come to the ground state unless some external disturbance is given to the system? So, in coming from the excited state to the ground state, this process must be induced according to Bohr's theory. In fact, spontaneous emission was assumed at the time as very common, but after the advent of Bohr's theory, spontaneous emission according to Bohr's theory is not. According to Bohr's theory, should be. Okay. Using this and calculating the rates for absorption and the emission, ultimately Einstein was able to derive Planck's equation. Now, absorption reduced rate is written as some number of photons, density of photons, and some coefficient P1, 2, they are sometimes known as the Einstein P coefficients. This is only one mechanism for absorption. For the emission, there are two mechanisms. One is induced process and the spontaneous process. For the induced process, similarly as absorption, we write instead of B1, we write B21 is coming from 2 to 1 into number of molecules into light density, and spontaneous, that is independent of the density of light. So this B coefficient and B coefficient have the same significance. A coefficient is something different. And in deriving the Planck's equation, Einstein had to assume that A coefficients and B coefficients are related by this equation. They are related. Okay. Spectroscopy and photochemistry. Molecules per photon to molecule, this is the process taking place in spectroscopy. Light-induced transition between the stationary states, this is the main thing. And photochemistry, where chemical reaction takes place in presence of light. Now we know that photochemistry is the reaction in the excited state. Ordinarily, when we consider the reactions in the laboratory, in absence of light, that means the reactions are not modified by the presence of light or normal reactions. That is done in the laboratory, they are thermal reactions. And photochemical reactions take place in presence of light. Now consider one law of photochemistry. First law of photochemistry, sometimes it is called the Bronsted-Dapper law. Bronsted-Dapper law states that the molecule, those lights which are absorbed by the molecules are only effective in producing chemical reaction. Now we know that light, when absorbed by the molecules go into the excited state. So the light first excites the molecule and then the reaction takes place in the excited state. This is in contrast with thermal reactions. Is some description of interaction. We have spectroscopic transition as M1 plus photon equal M initial plus photon equal to M final. And if this is a process, we can apply the law of chemical kinetics here. The rate of reaction, it may be dm1 concentration pt or d of n dt, where n is the concentration of photon, that is the number of photons per unit volume. So we write minus dn dt as it disappears from the system, equal to some constant as we write for chemical reaction, the rate constant. But Einstein wrote in place of k the term b coefficients, b, the concentration of n into n concentration of photon. This is very simple, true for electric chemical reaction. Then after some manipulation, we arrive at this. That's law Ln is the number of ions per unit volume of photon incident on this, and IT or Nt is the number of photons per unit volume transmitted light, equal to that, which gives us log I0 by I equal to epsilon A. That means if we assume that this is a chemical process and we apply the laws of chemical kinetics, one can ultimately arrive at the very famous law, Debasish's law. This is true for every spectroscopic process. Another interesting thing is that log 0 by I is infinity, as you know, but here in this we have some k by t. This k is related to the coefficient actually. So experimentally one can determine epsilon, and Einstein's B coefficient can be calculated theoretically using quantum mechanical perturbation theory. So here we have a platform where one can measure a quantity experimentally and compare with the result obtained of the calculations. This is the relation. So we said the spectroscopic transition is transition between two stationary states, initial state and final state. It's a very uncommon convention to write the initial state on the right hand side and the final state on the left hand side. In thermodynamics, what we do always, we write the initial state on the left hand side and then put a arrangement in the left to right. Here it is given the opposite direction. Very clear thing as practiced by spectroscopists. Okay. Now, initial state of molecule or matter, that is the substationary state, it has some wave function. We all know that any state has every stationary state is associated with a wave function. So final state is also associated with wave function psi a, and interaction is taking place so that it goes from initial state to the final state. Interaction is something which is happening, and in quantum mechanics this is represented by means of some operator. In property we have operators for everything. For energy you have an operator, for momentum we have an operator, for angular momentum we have an operator. We have similarly for interaction we have an operator. So we have initial state, final state and operator. So the probability of the process, whether the process will take place or not, or to what extent the process will take place, this will all depend on these three quantities, on the psi I, psi f and this operator. And it can be shown using quantum mechanical time-dependent perturbation theory that this transition probability is proportional to this quantity, psi I and psi f. In between them there is the operator. We integrate this thing about the whole space and take the modular square. Modular square is taken physically. Why modular square, right? In theory, but physically, what to say that these wave functions can be real or imaginary also, complex. If the wave function is complex, then the value of this integration, value after the integration may be complex, but the probability cannot be complex. Probability is always a positive definite quantity. So if a quantity is a plus ib, from even a plus ib one can get root over a square plus b square mod of a plus ib, which is some positive definite quantity. Now if this probability is equal to 0, if this quantity is equal to 0, we say that the transition is not taken, will not take place. The probability will do. And if is not 0, this is an allowed transition. If is large, then there is a larger probability for transition. And this p equal to 0, that is the forbidden transition. Using this, that this p equal to 0 but this integral equal to 0, one can arrive at the selection rules. Every spectroscopic transition has selection rules, and this is derivable from this condition that this integral is equal to 0. Now, if we consider the process as m plus photon equal to m initial plus photon equal to m final. If we treat this like a chemical reaction, we know that during this process energy should be conserved. That means energy of the initial state plus photon energy must be equal to energy of the final state. So this statement is nothing but the conservation of energy. So epsilon f minus epsilon I equal to h. So this is nothing but the Bohr condition. So Bohr condition is nothing but the conservation of energy. Now look at the left hand side. Left hand side is epsilon f minus epsilon I, energy of matter in the final and initial state, different. So that part depends on matter. This part depends on matter, and this part depends on light. Because this appears, this arises due to interaction between matter and light. So the left hand side depends on matter, the right hand side depends on light. It's interesting. So different types of energy levels. We know the gap between the vibrational energy level is different from the gap between the rotational energy levels, or gap between the electronic energy levels is still different, gap between the nuclear energy levels is still larger. So different types of energy levels can be monitored by using lights of different frequency. If this is different, if this part is different from, then mu should be different. Now in the case of electromagnetic radiation or light, we have, in one extreme we have radio frequency or radio waves, and these are longest wavelength and shortest frequency or shortest energy, and on the extreme is the gamma rays, where it is the frequency, highest frequency and lowest wavelength. Now radio wave, then this electromagnetic spectrum can be classified, divided into several regions. One is the radio wave region, the microwave region. Microwave we all know, this is entered into the kitchen. Then infrared, visible, the visual part, ultraviolet, X-ray, the gamma rays. It is interesting. This part, radio wave and microwave, one Indian physicist is pioneer in this field. His name is Debasish. 30th November, last 30th November was his birthday. And associated with each region, we have different types of spectroscopy. In the radio wave region, we have NMR. In microwave region, we have ESR, anti-rotational spectroscopy. In the infrared region, we have vibrational spectroscopy. In UV and visible region, we have electronic spectroscopy. In the UV and X-ray region, we have photoelectron spectroscopy. And in the gamma region, we have Wolfram. Each region associated with the characteristic spectroscope. Skip. There is another thing which is known as down spectroscopy. But what I try to emphasize is that any spectroscopy like NMR, ESR, EPR, vibrational, rotational, or anything, gamma spectroscopy, that can be represented as transition between the two stationary states. But here, that means we require a light of definite frequency. to bring about this transition. But Raman effect cannot be represented like this. Raman's effect is actually a scattering process. In fact, when Compton discovered the Compton effect, that is the scattering of electrons by X-rays, when the result was published, people knew about it. From that time, from 1923, Raman had an idea. He thought that if this is this process that is taking place with electrons, there must be some optical analog for this. Using ordinary light, visible light, one can have this effect. And we know that he tried for long 5 years, and in 28 February of 1928, this effect was discovered. And this, that's why 28 February of every year is observed as the National Science Day in India. Now, Raman effect cannot be presented like this. Okay, I will come. What is Raman spectroscopy? Is an elastic scattering. The process you can write as chemical reaction at initial material state. They are colliding, reacting, matter in the final state and the photon in the final state. And that means there is a collision, the exchange of energy between the photon and matter. So we have epsilon F minus epsilon I. If we apply here this law of conservation of energy, we have this equation, and after some rearrangement we get this equation. That means epsilon F minus epsilon I, you can do this. And if epsilon F is greater than epsilon I, that means the dy is greater than df, or delta I is equal to delta delta I. That is, wavelength of scattered light is greater than the wavelength of incident light. This is known as Stokes lines, and the reverse is known as the anti-Stokes lines. And the transition, one can represent the transition like this. This is the, suppose these are the vibrational levels. These are the vibrational levels. If one goes directly from this state to this state, this is a vibrational transition. This will appear in the IR region. That is, the IR light is required to bring about the calculation. But in the case of Raman transition, it starts from the initial state and goes to the final state. It starts from the initial state here and goes to the final state, this or this, but not directly. It goes via some intermediate virtual state. Just by when light interacts with matter, it first goes to the virtual state. And virtual state is not a stationary state, it is a non-stationary state. So it will immediately decay to a stable state. It is coming to a stable stationary state. That means it is going from one station to another via some other station. So it is like going from Howrah to Bandel via Bandhavatu. Instead of going from Howrah to Bandel directly, one goes from Howrah to Bardwan via odd line. Bandel doesn't appear there. And then from Bardwan to Bandel. This is via some intermediate state. Another interesting thing is that you said that this is depends on property of matter. If this is difference in vibrational property, this will depend on the vibrational characteristics of the matter. For example, the force constant. So, measurement of the vibrational spectrum will give information about the force constant or the bond strength. Similarly, if these are the energy different with the rotational levels depends on that means it depends on the rotational characteristics of the matter or molecule. So it depends on the moment of inertia, which is a rotational characteristic. And from moment of inertia, one can measure the bond length. So it depends on if it depends on the electronic property, we shall come. Before proceeding further, we initially pose some questions where this type of reaction, there is light plus molecule equal to molecule, or molecule plus light equal to molecule, or molecule 1 to molecule equal to light, or etc. This thing. Let us see whether this is. Light plus molecule 1 giving molecule 2, this takes place. Vitamin A, this is converted to cis-retinal. Vitamin A is a retinol actually. This is converted to cis-retinal, and in place of light, when it hits the cis-retinal, this is converted to a trans-retinal, and this process, this photochemical process is responsible for our vision. Here, in the photochemical process, that is cis-retinal plus light giving transmission. That is the cis-trans transformation. Cis-trans transformation is not possible thermally, because when you have a double bond, and in order to make a cis to a trans, one must have a rotation about the double bond. That is very difficult. But as long as we have a double bond between C and C, the rotation is high rotational period. But when we excite the double bond, there is one of the pi electron is transferred to the pi star state. Then what happens? Initially we have 2 electrons in the pi and no electrons in pi star. So bond order equal to 2 minus 0 by 2, that is equal to 1. That is pi bond order is equal to 1. 1 pi bond. But when you excite one in the one in pi and another in pi star state, then we have the bond order equal to 0. For the definition, bond order equal to 1 minus 1 divided by 2 equal to 0. That is, in the excited state, pi bond in this sense doesn't exist. And in the excited state, since the pi bond order is 0, then the rotation is possible. Rotation is possible, so system transformation is possible. Only if it proceeds to excited state. Photograph. Molecule plus light 1, molecule 2 plus light 2, where we know processes like fluorescence and phosphorescence, where molecule absorbs the light, goes to the excited state, and one doesn't like to have this extra energy for a long time. Human being doesn't also like. Molecules also like, doesn't like, they come to another state and producing some light. This is a process possible. Again, molecule 1 plus molecule 2 molecules giving light. This is possible, actually, plus some energy. Here is the process of bioluminescence, for example, bioluminescence. The molecules that are produced due to reaction, they are in the excited state. And the excited state molecule emits energy. Extra energy comes as light, and example as fire, this type of reaction takes place, and that goes to excess there. Light plus light forming another light. But this type of experiment that is done. Suppose we have a light of frequency 800 nanometer and two 800 nanometer photon can produce one photon of wavelength 400 nanometer. The process can be, suppose we have a batter here. Suppose we have a batter in this state. If it absorbs two photons of h nu, say, which gap is this? It will ultimately go to this state. This is the non-existent state, this is the virtual state. So, from this state, h nu, by absorbing two h nu, one h nu here, another this here, it goes to this state. And from this state, when it comes back to this, it is h1 and mu2 equal to twice mu1, just for conservation. This experiment has been done, and this is known as second harmonic generation. Similarly, if it is h1, nu1 and nu2 and then h nu3 will be produced, like nu1 plus nu3, this sum generation. So this type of processor possible. Here, this process is much simple, like light plus light equal light. It requires the intermediary of atoms or matter. But the matter ultimately comes to the same state, initial state. That means the matter acts or plays the role of a catalyst, if I say. So spectroscopy deals with transition between two stationary states, conventional, and there are different types of spectroscopy depending on the frequency of light that we emit. And in every case, in each case, one gets information about the states of matter. Spectroscopy is another important aspect. It is a dynamic aspect also. For example, if there is a transition between these two states, epsilon 2 minus epsilon 5 minus epsilon initial equal to h nu, this is the conservation of energy. Not only that, it requires some time for photon to go from this state to this state. And the time, this is the time scale associated with spectroscopy. This time scale, or tau, is approximately h by delta E. Delta E and h by delta E, this is the time scale. So this delta equal to h nu. So time scale is, we know that in enema this uses very short nu, shortest nu. So is associated with this larger time scale than, for example, in IR process. IR process, nu involved in the IR process is less than the nu associated in electronic transitions, visible, invisible spectrum. So the time scale for the IR transition will be higher than, if it is lower, it is better. Will be higher than the time scale in the case of invisible. So every spectroscopic process is associated with time scale, and this time scale, utilizing this time scale, one can measure the dynamics, the motion of the body, the state of motion of the molecules. That means there is a process taking place in the molecule, which is a time scale. And in spectro, we are using a tool which has this time scale. So, if the time scales are widely different, suppose during a time, the spectroscopic transition takes place, the time scale associated with the molecule is larger. That is, the molecule doesn't change during those time, so you cannot measure the dynamics. But if it changes the state, the state of the molecule state in the state during that time, then we can determine the dynamics of the molecule. Dynamics that is taking place within the molecule. So, in order to have idea about the information, idea about the dynamics taking place inside the molecule, one has to choose the right spectroscope. One example is that when light absorbs in the visible region, some ground state, excited state, if it goes, this of the order of femtosecond. This is an equilibrium state. This is not an equilibrium state because during this time, very short time, electron only moves. Nuclear framework doesn't move. So initially, the electron framework, electronic distribution and the nuclear framework was in equilibrium. There is nuclear framework and electronic distribution, they are consistent, compatible. But as soon as the electronic distribution changes, electron jumps from one place to another, electronic distribution changes. But the nuclear framework doesn't move. So nuclear framework remains the older one, but the electronic distribution is changed, so these are not compatible. So this is not in equilibrium. This is not an equilibrium state. It is sometimes called the Frank Condon state. It takes around 15 seconds. Then this is a non-equilibrium state. And when you create a non-equilibrium state, what we do, what happens is that any non-equilibrium state, we try to come to an equilibrium state. This process is called as relaxation. When we absorb some extra energy from the surrounding, we get excited. And when a particular person gets excited, what we say is relax. Relax means come down or try to give up the excess energy that we have spent and come to a stable state. This state is known as relaxation. This is the relaxed state. And then again from this relaxed state, it comes to the down state, but not this equilibrium state. Any spectroscopic transition will lead to a non-equilibrium state. So this is a non-equilibrium state, sometimes called a Frank quantum down state. And then it relaxes to this. This is the complete. If this relaxation, if it is a gas phase thing, then many molecules are far apart. So this relaxation involves geometric change inside the molecule. This process takes place in solution, and surround the molecule there are solvents, and during the time the electronic transition takes place, the solvents will not move because they are heavy. So these states, the fractal state, the solvent, the solvation shell here and the solvation shell here have the same geometry, same arrangement, but that is not consistent with the electric charge distribution or the dipole moment produced. So solvent molecules will reorganize to form this relaxed state. So this relaxation includes two relaxation. One is the internal relaxation that takes place within the molecule, and other is the solvent reorganization. And this solvent this process is of the order of this time scale for this process is 10 to the power minus 12 seconds. And when it comes to this state, you can emit the fluorescence that is produced is of the order of 10 to the power minus 9 seconds. So for this 10 to the power minus 15 seconds, the instant is almost this time scale to a time scale 10 to the power minus 9 seconds. That means 10 to the power 6 times greater than this 10 to the power 15 seconds. 10 to the power 6 times. No stroke to do. So during this absorption and emission process, or sometimes called the fluorescence process, during this fluorescence process, we can have different time scales. So we can measure different events which matches the time scale. This is one thing. Another thing that I written here, I just have to discuss. The first thing that you have to shine matter with light. So, a source of light is important. What is the source of light? That depends on whether we use radio frequency or microwave frequency or any other frequency, visible light, etc. But usually what is done, light of a particular wavelength or the monochromatic light is used for this. And nowadays, with the discovery of lasers, we have a light. Laser lights are highly intense. Here, the conventional sources, the light density, the photon density is not very high. In the case of laser, photon density is increases, and if the photon density increases, the probability of absorbing 2 photons or 3 photons at a time or multi-photon absorption, it also increases. So, if you use laser light, other possibilities open up. Possibilities like biphotonic absorption or multiphotonic absorption. And this type of absorption process finds application, for example, in isotope separation. A photon is characterized by its momentum, h nu by c. Momentum has three components, px, py and pz. And another property is the polarization of photon. So these are the four numbers that is required to describe a photon. In laser light, all the photons have exactly the same four numbers. Photons do not have to obey power distribution principle, they are themselves. So, power distribution principle is not applicable here. All the photons can be in one state, and that's why this property, coherence property appears. They are monochromatic, light of precisely definite wavelength, and they are polymetric. They are not diverging. When you put with the torch, its light goes in this fashion. That is, if you observe a torch here, the circle produces this ball, and that wall, the circle will be much better. That means it diverges. But if we use their laser light, let's try. Same size. And if you see, almost the same size. So here there are lasers. Now, last part. Acronym part. Every lecture should have an acronym. First, I owe directly to Professor Mihir Chaudhary, my research supervisor, who introduced me to the subject of spectroscopy. Then I actually thank the organizers of different special courses and workshops that helped me to prepare the slides as the topic. And lastly, the research scholars at Purdue University, either Kolkata and Presidency University, because I am not very smart in using these laptops and all these facilities, modern facilities. Research scholars are very familiar with these laptops, much smarter. So whenever I have to give a talk, I depended on them. I just sketched the subject matter, and they prepared the slides for me. And lastly, thank you. It needs special mention because a lecture for 1 hour 30 minutes or 90 minutes or 19 to 60 seconds, really, here it is very evident that time is relative. To me, who is giving the lecture, time comes. And to those, the audience, you, time sits on you. And you are just thinking, oh, Pakon Shishabi, Pakon Shishabi. So, but you have listened to this with very patience, so special thanks to you. Thank you.